work, right? It works for me too. Got our studio working. All right, so you must not have been exposed either, or had a negative test.
Yeah, I think you guys have gone to that very.
You luck out.
I don't think that's
Huh?
I don't think that means it either.
I think you.
Did she?
Yeah, at least like self-taught.
All right, let's see here. We are doing ANOVA, plant growth. So we did QQ plot, plant growth. All right, so all of the computers here have been updated, and we've gone back and forth this week trying to make sure everything works. Looks like it works. I emailed IT yesterday because I came in and checked 2 computers. They worked. Both of them worked for me. Then I sent out that announcement. No one emailed me, so either you didn't have a problem or you guys didn't come in and work on a Thursday. I don't blame you. Thursday night. But anyways, here's why this is important. So we talked about QQ plots, and last time, without the update, this did not work. We had to do all of our subsets to get our QQ plot to work, but now I can write the formula, and QQ plot function now will make all of the QQ plots together. All right. Now I've zoomed in to make this text bigger, but there are ways you can move the windows, reorganize the windows, so that you can actually view it a little bit, or you can actually type it in down at the console and run it. So figure margin's too large. There must be some issue with the plot device windows. I'll have to figure it out. It works for me. Had to change that. But anyways, that's why we do it. So that way,
Whenever I try and update, not update, but whenever I try and rename my data, maybe we start a new section. Okay, so not rename it.
very close. Unexpected bad allocation.
And it just keeps making me restart.
That'll work for me. Same for you? Yeah.
Oh, you were.
We encountered a fatal error. It said bad allocation, right? Is that right?
Yeah, I'm just gonna keep going
Oh. Here, hold on. Let me run this. Geez, more problems.
I don't know why yours is working. Why is it?
So I ran all of those. Let's just do this. Run all chunks. Yeah, it seemed to work for me. Oh, error. Mod 1 not found. How come it didn't? Oh, maybe. Let's do this. Run all chunks below. Oop, error. Height and test. How come that did not work? Yeah, that works. Height is a function of test. That's my box plots. T-test. All of this works. How come? Finite. Oh, hold on. You know what? I know what it is. Huh. I know what the issue is. Strings as factors is read in incorrectly. Let's see here. Header equals T. Oops. Strings as factors equals T. Now let's try that. Try that one more time. Strings as factors. That works. There it is. That works. Yep, definitely that was not gonna work. All right, so QQ plot, plant growth. QQ plot, plant growth. We did the subset, so it all works for me. So where does it stop?
Mine isn't. It like runs everything, but it's almost like after a certain point in time, it kind of just gives me a fatal error.
Okay.
I mean, usually I don't get past the functions.
So we're working, so load the library.
Okay.
And what you can do,
I haven't done it yet.
Calvin, yours is also doing the same thing? Yeah. How about, do you have anything that you were working on? Could you restart the computer? What we'll try is, restart the computer and see if it works. And then
I don't know. I don't know Alex is getting it. I know Jeff got paid.
what was the error message?
Just said fatal error.
Yeah, it said allocation of
bad
resources.
Bad allocation.
It was bad exception, bad allocation, right?
I think it was just bad allocation, something like, yeah.
We'll see it and we'll get it. That emailing IT to get this fixed. In the meantime, I think we can kind of minimize what chunks we run so you can actually work with it. Oh, you can also, you restart, did you restart too?
Yeah, I'm restarting.
Okay. We'll restart it and then we'll get that error message and we'll finish it. So while we're doing that, we'll continue because it just seems to be the computers and we don't have a whole lot of people with their own, with the regular computers. So I want to just continue on with our post-hoc tests. So I created my model, right? We run our ANOVA to get our ANOVA table. We know the means are different, and now we need to do our post-hoc test. All right? So our post-hoc test. All right? So post-hoc test here that we're going to deal with, we've got two to choose from. All right? Tukey's HSD and Dunnett's. All right? Tukey's ASD that we're going to run. Is probably the #1 post-hoc test that will be run. This test runs all pairwise comparisons to determine which means are different. All right, so all pairwise comparisons. The second one Dunnett's multiple comparison test. All right. The second one compares treatments to a control It does not compare the treatments to each other. All right? Does not compare the treatments to each other. So if we're comparing the treatments to each other, we will run a Dunn's and do a control versus treatment 1 and then control versus treatment 2. Now, what's the purpose of these post-hoc tests? Well, we're trying to figure out which means are different. We use a post-hoc test to control for inflated type 1 errors. All right? So inflated type 1 errors, is it still the same message?
Yeah, just keep, it says our session aborted.
So that first one that said restart the session, I want to see that first window that pops up. Unexpected exception, bad allocation. Accepted exception. Fatal error. Unexception. What was it?
Unexpected exception.
Unexpected exception. Bad allocation.
Bad allocation.
That's sent off to IT. Maybe they'll show up. He might ask me to try it out. All right, so back to here. Type 1 inflated error, or inflated type 1 errors. That's what we're trying to control. So with our inflated type 1 errors, we said every test that we ran has an alpha level of 0.05. If we run 2 tests on the same data set, and that's kind of key, on the same data set, each one has a 0.05 type 1 error rate, but when we ran both of them, the collection together now makes the overall error rate higher than that 0.05. And with each additional test that we run on the data set, we keep increasing that error rate. All right? So these post hoc tests control for inflated type error rates. While each test has an alpha, alpha equals 0.05. If we run 3 tests on the same data set, the same data, then our alpha is greater than 0.05. A post hoc test, overall alpha is 0.05. So, and that's why we're doing. That's why we run these post hoc tests. Why we don't run just a series of pairwise ANOVAs or pairwise 2-sample t-tests. All right. So Tukey HSD is really easy. All right. The function is Tukey HSD AOV of our model, where model is our linear model. All right. So I already made mod 1 to obtain our HSD table. We run Tukey HSD, note the capitalization, AOV of mod 1. And I run that. And these are the comparisons. All right. Now, for this Tukey's, we're doing all pairwise comparisons. So on this data set, it's pretty easy to say the only means that differ is treatment 1 and treatment 2. But I've got the output there. What if we have more than 1? Or more than 3 groups? What if we have, let's say, 5 groups? It makes it really difficult to identify. So if we have more than that, let's do this, function mean. The way we go about doing it is look at our means and we arrange them from smallest to largest values. So TRT1, then we have CTRL, and then TRT2. All right, so I've arranged them from smallest to largest means. And then what I'm going to do is look at my Tukey's table, which is located down here. Leave that open. All right, and I would start doing my comparison. And what I do is I do this comparison first, smallest to largest. So treatment 1 to treatment control. Is there a difference? No, it's not. The p-value is 0.39. So what I'm going to do is draw a line over top of them to indicate that these means are not different. And then what I'm going to do is do treatment 1 versus treatment 2. Treatment 1 versus treatment 2. Is there a difference? Yeah, there is. So my line's going to stop here. All right? So any point where the lines are underneath capture something, then it's there's no difference in the means. Now, why do I continue going this way? I continue doing it to see where my break is. Figure out where I have to break this line. Now, I've already found that. If I have this break, so then our next test is to say, well, I know treatment 1 and treatment 2 are not similar. What about control 1 versus treatment 2? So now I look at my Tukey table, it's 0.198, no difference. So I draw my line, so I draw a second line right there. So values, groups that have a line over top of it mean that the means are similar. Groups that don't have a line, or don't share a line, are different. The ones that don't share a line are treatments 1 and 2. Now, for 3 groups, we don't really need to do this. All right, it's pretty easy. But if you have 5 groups, let's say, now you've got, just to kind of demonstrate it, I've got A, B, C, D, and E. All right, our Tukey's is going to run each of these pairwise tests. So we're going to have a total of 10 different p-values. And you're going to be looking at this big table and saying, I have no idea how to compare it. Arrange them, smallest to largest, and just go down the line with your comparisons. All right? So that's the easiest for Tukey's. And that's probably going to be the one that you run, Tukey, HSD, AOV. We can also use Dunnett's. So here's our Tukey HSD. That's the one that we run. And Dunnett's is a special case. We do have them. Sometimes you're going to use it. Sometimes you're doing a study where you do use that. But most of the stuff that we're going to do, we're not. We're just going to focus on our Tukey's. All right? So here's how we run. We'll pass through Dunnett's. You can work through it. If we come back to it, maybe a little bit. But our exam's on Monday, and I can tell you that we don't have Dunnett's on it. So we're going to try to get through. So I asked you to do this, fish length. All right, so did you do it? Work through it? So let me work through it right here so you can see how I did it. So what we need to do is we're going to start fish length. Go down here in posthoc test. We might return to it after our exam. Probably not, though. FishLength.txt. All right. I'm going to read in my data set, import data set from text base, documents, ASU, stats R, data, FishLength. All right, check it out. Yeah, heading is true. I'm going to do strings as factors. I think that may be standard now, but I'm going to make sure I check that. So that way, when it reads the strings, it's going to read lake as a factor. It's going to key it as a factor, which will make our plots and everything work properly. Hit import. I've got my code. Make sure I copy that. Get it into ANOVA. And we kind of set up that this fish length data set, we measured length of fish in different lakes. So our question is the mean lengths of the fish different between the lakes? Or we could say, does lake have an effect on the average fish size? Either one. All right, so if we look just at our data, all right, looking at our data, I'm going to look at summary of our fish. I'm going to call it fish. I'm going to call it fish data. Fish data instead of fish line. I'm going to call it fish data. So I'm just going to look at the summary of fish data just to see what kind of data set I have. Now, I knew when I did the experiment, I have two variables. I've got lake, and this is my summary. So I've got, these are factors, qualitative data, they're groups, categorical, nominal data. All right, I've got 5 of them: big bear, deer, green, mallard, and ram's head. And I have length, which appears to be a continuous type of variable. So now what we want to do is we've looked at what type of data we have. I know my names. I can see it's lake and length. So I'm going to plot length as a function of lake. All right, so I can eyeball it and see what it looks like. So I look at my bar plots, and not everything's labeled. Right, that one kind of falls off. And again, I could increase the size to get my labels, but I'm looking at the bar graphs, or these box plots. So number one, am I going to be surprised if I get a p-value that's less than 0.05? Probably not. Probably not. All right. I'm seeing variation here. I've got some that are big. I've got some that are small. When I look at the interquartile regions, all right, I can see some where the IQRs, they don't overlap. So I'm kind of expecting to find a difference between these two versus this one and so forth. So kind of just looking at the figure, I'm not going to be surprised if there's a difference. Second thing about this figure is that I don't see any obvious skew. All of the medians appear to be mostly in the middle or close to the middle of these interquartile ranges. So when I run my tests, or when I run my assumptions or check my assumptions, I'm not finding a significant, I wouldn't be surprised if they're all normally distributed. All right? We don't see skew either. So, I'm sorry, so we already talked about the skew. We don't see the unequal variances either. So if we had unequal variances, we would get different sizes of both our whiskers and our interquartile ranges. All right, but when I look at them, yeah, I see some variation. This one's probably the smallest one. This one's probably the largest one, but this is maybe 60% of the size. Maybe I'll find a difference. Maybe I won't. Maybe it's just an even range. So maybe there's unequal variances. Maybe not. I'm not going to be surprised if I find it either way. It could be a p-value someplace between, say, 0.01 and 0.15, kind of in that range. Lastly, outliers. I do see some that are out, but not, they're not like way down here or way up there. They're close to the 1.5 times the interquartile range. So our goal is to run an ANOVA. We've got one categorical independent variable, that's our lake. We have one continuous measurement variable, that's our dependent variable. All right. So ANOVA is going to be the test that we want to run. So we want to run an ANOVA. First, check the assumptions. So I'll tell you that when we did this experiment, we already did a random sample. We randomly sampled the fish in our lake, so each data point is random and independent of the other. So we met the first assumption, all right? Normality assumption. Gonna run our QQ plots. Now we can do our subsets, or update your R, try to get it working. I'm gonna run length as a function of lake. All right, length is a function of lake, data equals fish data. Write the formula, and the QQ plot function from the car package, comma, will produce all of the plots that we need. So I'm going to enlarge this just to kind of take a look at them. And yeah, they're small. I mean, the data points are small, but they're all seem to be captured by our confidence envelopes. If we wanted to look at them a little bit more closely, we can probably use subscripting. So subscripting, remember in our loop we had brackets and then the I. I'm curious if we can do bracket 1. The first one is Big Bear. We'll put bracket 1 and see if we can get just the Big Bear. No, guess not. Let's try 2 brackets. That'll work. No, still not. I'm sure there's a way to do it. Let's see what it gives me. No, still. I'll do some searching, see if we can figure out how to use this function, but then pick out which QQ plot we want to look a little bit more closely at. But right now, it looks like everything's looking good. Nothing is out of the ordinary. So right now, data appear to be normally distributed within each group. So again, that's our assumption, within each group. And thus, we'll use Brown-Forsyth to check the equal variance assumption. So Brown-Forsyth, remember, is lean test. Length as a function of lake. Data is our fish data. And center equals median. Median. So, based on this, do we have equal variance? Yeah. So remember, our Brown-Forsyth is testing the assumption. The null hypothesis is that our variances are equal. Our alternate hypothesis is that they're not equal. All right? So variances appear to be equal, because our p-value is greater than 0.05. So we are good to go with running the ANOVA. All right? So our linear model, I'm going to call it fish mod. I'm going to create my linear model where we are trying to predict length as a function of lake. Those variables are found in the fish data dataset. So we're going to create that model and then generate our ANOVA table. All right. I'm going to run that. Did I need to look at the summary? No, not at all. Didn't need to. No. Summary was presented to kind of show you what all was there, to show you some of the similarities. All right. If you got a table, an ANOVA table that was like all zeros or null or something like that, yeah, look at the summary and see if the summary gives you anything. If the summary doesn't give you anything, there's a problem with your data set, probably with the import. But here's our table. We got our F statistic, 15.161. We've got our degrees of freedom, 4 and 249. And we've got our p-value of 4.16 e to the negative 11. Really small p-value. So, are the means equal? So based on our ANOVA analysis, our ANOVA table, we know at least one mean is different from the rest. So does length affect our fish lengths? Yes, it does. But we're not done yet. We need to know which ones are different. We need to know which ones are different. So since we're interested in all pairwise comparisons of our lengths, we're not doing anything versus a control, our next step then is to use Tukey's. All right, so our next step is to use Tukey's to determine which means are different. So I'm going to use Tukey HSD on the AOV, the ANOVA table, the ANOVA data, I should say, the ANOVA sums of squares and stuff, of our fish mod, which is our linear model. And I get this. All right. Now, how do we summarize it? Kind of a task. It's a daunting task. Got a lot of rows. I see some values are less than 0.05, some are large, some are small. How do I go about kind of summarizing this in an easy way? I'm going to use just what I showed you. So I'm going to go down here. We're going to calculate the means by the lake. Which function do we do that with? Aggregate. All right. Aggregate function allows us to apply a function to a variable. The variable that we want to apply the function mean. So that our function is going to be mean. We want the mean applied to the length variable, and we want to do it for each of the levels of lake. All right, so aggregate, we're applying the function mean to length for each of the lakes in our fish data set. All right, there's our average lengths. And then what I'm going to do is take those lengths and I'm going to arrange our lakes in order from small to large. So our smallest one is Ram's Head, RH. Next one is Green. Next one is Big Bear, BB. Next one is Mallard. No, that's it. I can take that back. Mallard. Mallard is next, and then Big Bear, and then Deer. All right. Move this over. Those of you at home. So I arrange these numbers from smallest to largest. I've got Ram's Head, Green, Mallard, Big Bear, and Deer. And then I'm going to go up to my table. Move that just slightly. Now I'm going to do my comparisons, and I'm always going to go from smallest to largest. All right. I can always start at the big. So, if there is no difference in mean, I can do Ram's Head and Deer, and I'm going to get a p-value that's greater than 0.05. And because these values, the most extreme values, are not different, then they're not going to be different to any value in between. Right? So if these three If I did Ram's Head and Mallard and there's no difference, because green's in the middle, that's not going to be different to either of them. It's like saying, what's the minimum difference that we need in order to find a difference? Well, if Ram's Head to Mallard isn't a minimum difference, then we know green isn't a minimum distance because that's less than our Mallard. So we're going to go small to large. We're going to start Ram's Head versus green. Ram's Head versus green, the p-value is 0.4457. Cursor, here it is. Right there, that's our first comparison. No difference, so I'm going to draw a line over top it. Then I'm going to go Ram's Head to Mallard. That's right below it. P-value is less than 0.05, the mean is different, so my line stops. Then I go to green and Mallard, because I need to know. I know Ram's Head and Mallard are different, but green's closer to Mallard. Let's see if that one's different. So I go Mallard and green. Oh, there's no difference. So now I'm going to start a new line. And now I go to green and Big Bear. Green and Big Bear. That one's not different. Green and Big Bear. Extend the line. And then I need to do green and deer. Green and deer, here it is. That one's different. So my line stopped. Now, I could go to mallard and deer, or big bear and deer. But what I'm going to do is do the big bear and deer first. I'm going to look at these two to see if they're different. Because based on the means, we had 0.191 and 0.92. Yeah, big bear and mallard, they're really close together. Our green was at 0.78. I know green and deer are not different, so I'm just going to go to big bear and see if big bear is different from the deer. See if I need to start a line that covers up those two. So I go deer and big bear. That's the top here. There's our p-value, less than 0.05. So I have a line only over deer. So the lakes that have a line are not different from each other. I should say, the lakes that share a line are not different. If the lakes do not share a line, then they're different, then their means are different. So deer is the only one that does not share a line with any lake. So the average fish length of deer is larger than all other lakes. How do I know it's larger? Because I arrange them from small to large. And the mean is different. Green, mallard, and big bear, the fish in those lakes appear to be similar in size. Their averages are about the same. Ram's Head and green, same thing. They're about the same, but we know Ram's Head and green, even though they're about the same, Ram's Head fish are smaller in size than both mallard and big bear. All right? So this gives us a way to kind of figure out and make sense of these big, complex Tukey's tables. Do you present something like this in a paper? No, we don't. How do we do it? Typically, we make it in terms of a figure. So what I would do is assign letters to the lines. So this line might be A, that line might be B, and that line might be C. And then I take my average length data, move this out of the way, and the standard errors, take it over to Excel so I can make a figure like this. And then from the figure, I add those letters, and those letters are basically a proxy for the lines. Now, why did I do it this way? I arranged it. You can arrange it any number of ways. You could have arranged the lakes in alphabetical order. You could have done them from north to south. It depends on what we're trying to show. In this case, I don't really care about the lakes themselves. I cared about the fish lengths. So it made a little bit more sense to arrange our lakes from smallest to largest. It also made the interpretation a little bit easier, because then I added letters to each of our lakes to signify which means are different from the rest. And I included that information in the actual text of the caption. So you make a figure. You've got a figure. I just called it figure 1. And I say average fish lengths plus or minus SEs. That tells me that these are standard error bars. All right. So average fish lengths plus SE for 5 different lakes, or for 5 lakes. Lakes with similar letters were not significantly different from each other according to a Tukey's HSD posthoc test. Notice, I gave an interpretation, I said what test was run, and I specified a p-value cutoff. So in this case, I said, similar letters are not significantly different, meaning all of those p-values are going to be greater than 0.05. So A and A, Ram's Head and Green, they shared a letter. They're not different. Green, Mallard, and Big Bear, they all had B. They all shared a letter. They're not significantly different. Deer doesn't share a letter with any of them, which means they're different. And then by extension, our p-value for all of those comparisons would be less than 0.05. I didn't report the p-value for every single comparison because I don't really need to. How I've kind of structured my interpretation, I did that implicitly. So, overall write-up, kind of walk through everything. Here's our overall conclusion. Here's one way in which I could write up and summarize our analysis. So, average fish length was compared between 5 lakes. Fish lengths appeared normally distributed based on quantile plots, and variances were equal. And I give my stats. As such, an ANOVA was performed to determine if average fish length differed between the lakes. A significant difference was found, so a Tukey's HSD posthoc test was performed. Fish were largest in Deer Lake. P is less than 0.05 for all comparisons. That tells me that every Tukey posthoc test that included Deer Lake was significantly different. Fish were smallest in Ram's Head. P less than 0.05 for all comparisons except with Green Lake. Average fish length was similar in Green, Mallard, and Big Bear. So, 5 things we have to report. Look at what I included. The test. Yep. Quantile plots. Brown-Forsyth, ANOVA, Tukey posthoc test. I included everything that I did. The interpretations and conclusions. Yep. They were normal. That's our QQ plots. Variances were equal. That's Brown-Forsyth. Their difference in means was found. That's my ANOVA. I gave the breakdown. I told you which means were different. That's our Tukeys. Test statistic. Well, quantile plots do not have a test statistic, so we didn't include them. Brown-Forsyth, there's our F value. ANOVA, there's our F value. All right, Tukey's doesn't have a test statistic, so we don't report it. Degrees of freedom, the only test that had degrees of freedom, Brown-Forsyth, ANOVA. Note how I use them in a subscript to show them. All right, and then p-values. The only one that didn't have a p-value associated with it was this quantile plot. I have a p-value for the Brown-Forsyth, for ANOVA, and then for all of our Tukeys. Questions? It's a lot. Kind of step you through and said, okay, we've got these 2 variables, categorical variable, continuous variable. All right? Categorical variables are independent variable, and we're trying to see if that variable has an effect on our measurement variable. So we know we want to run an ANOVA, or we think we want to run an ANOVA. We then have to check our assumptions. We have to go through, check our normality assumption. Based on that assumption, it told us which test to run, Brown-Forsyth or Fligner-Killeen test. All right? Then, after that, we then proceed to our next test, which was the ANOVA, if our assumptions were met. All right? So from the ANOVA, if it was significant, or if we found a p-value greater than 0.05, we stop there. No posthocs. The means aren't different, right? We stop. Means are equal. But if we get a difference, if we find that the means, at least one mean is different, we have to go that next step and run a Tukey's posthoc test, usually, to figure out our differences. What happens when we violate the assumptions? In some cases, we just proceed as normal. Other cases, we can't. All right? So,
Is it just that one lake has an effect on FishLength time, since we're about pretty similar?
What's that?
Just like looking at the question where it says, does lake have an effect on FishLength? And here, lake does, but
The lake variable. Does the lake variable have an effect? Yeah, lake does have an
Okay.
effect. They have different effects, but lake did have an effect on FishLength. Yep. Yeah, so go back to the original question. Does lake have an effect? Yeah, it does. It does. FishLengths differ between our lakes. All right, so ANOVA. All right, so I've released the ANOVA. ANOVA Part 1. It is this. This is your prep for the exam. So our exam's on Monday, right? It's set to go live at around 5 a.m. All right? Set to go live at 5 a.m. Yeah, here it is. We have the closed book part. I think it's 50 minutes. Closed book part. The actual theoretical part, which is, I think, multiple choice or multiple answer type questions. I don't remember if I have any sort of, I don't think I have true, false, or fill in the blanks or anything. And they're going to be like definitions, interpretations, assumptions of the tests, choosing the test. So here's a scenario: which test will you choose? And it covers all the tests that we've done. So z-test, one sample t-test, Shapiro-Wilk test, sign test, Brown-Forsythe, Fligner-Kleene, and ANOVA. I didn't include Tukey's or Boson or Dunnett's. So several of those where I described what data we collected, what we're interested in testing, and then you tell me what test we run. All right. So, and then after that we have closed book. Closed book. The theoretical part, the R markdown stuff. That's going to be uploaded, I think, by 11 o'clock. And to kind of get you some more practice on ANOVA, I have this. All right. So the one, Gambusia is probably the most relevant one because we are asking for, does average length of the female fish differ between 4 months of collection? So what you can do is use the subset command to pull out all of the female fish. All of the female fish. How did we do that? Find my R. We will do that real quick. I know we're running out. So let me import my Gambusia dataset.
Did we use it on the fish data set? Practice video?
Well, I don't have different sex for the fish data. So biostats are homework. No, I think it's our data. Gambusia. There it is. We're gonna call it Gambusia. Strings as factors. There's our sex. So sex was M and F. So if we were looking for a subset of that Gambusia data set, all of the F right? We are going to use, I'll save it as females. We're going to use our subset function of our Gambusia data set where, you can call it sex, where our sex variable equals, double equal sign, and our quotes F. And I run it. I created a new data set, females. Has all of the same, all right? And it reports 2 levels, F and M, but I'm going to show you, if I just type in females, it is all females. all female fish. So you're gonna be doing that. That was kind of to give you more practice with subsets, something different. But it's all female fish, and then you're gonna look at length, fish length. All right. So work on it. For the second problem, this was supposed to use Dunnett's. Work through your ANOVA. You can try 2 keys just to make sure it works, but work through it by Monday. All right, so that way if you have questions, if you ran into problems, we can answer it during class at 11 o'clock. We won't meet for lab at 2. We'll be in here, or I'll come in here. If no one's here, I'll be down at my office, but we'll be available from that 2 to 4 time slot in case you have questions about the R markdown stuff. All right? Go up to ANOVA and the 2 keys. All right, we're good. I'll make the due date for this Monday, just so it appears on the calendar, and those of you that use the calendar will see it as, oh, it's due today. And what I'll do is I'll do like first thing in the morning. I'll do it by 11 a.m. Well, I guarantee you that no one's like, if you're not watching the video, I'm gonna guess they didn't.
Some people are just gonna see Monday and not even check that 11 a.m.
They're gonna see it's due, well,
Not me. Oh no.
those people probably don't even realize that we have an exam on Monday either.
Should yell, get in the mic, Beastie Boy style. Should be like, you got an exam.
I had the due date, and it,
Matthew's rap video. So has that ever happened before?
sure.
That fatal error that was going on, that's weird. It was
That's